Yep.
Okay, great. Well, good morning and good afternoon, everybody, and thanks for attending Lehigh Energy System Engineering ongoing seminar. My name is Andrew Coleman. I actually work for the Electric Power Research Institute and started this program over a decade ago. And we've had over, I think, 257 graduates from this program since 2008. And we also have this wonderful webcast series that we've put together. And Rudy's been really shepherding that for the last couple of years. So we've had some really outstanding talks. And I also teach an energy systems course in the summer for Lehigh. So some of the students were my students this summer. So today we want to introduce Deepak Ramasubramanian, and he is our senior engineer scientist for grid ops and planning at the Electric Power Research Institute, and he works in our power delivery and utilization area. So he's going to talk today on DERs, distributed energy resources, and all the challenges with both modeling and parameterization of models and transmission systems. And some of the challenges that you will hear about in today's presentation will be some of the things you read about in some of the IEEE magazines and all the power gen magazines. I mean, the things that he's going to go over are some of the biggest challenges out there right now. And I know he'll offer a couple of solutions in this area that we discuss all the time at EPRI, and maybe even cite some case studies. So Deepak he's a senior engineer at EPRI, like I said, and he joined in 2017, and he's been doing modeling, controls, stability analysis for bulk power systems. And he's, I guess he's done a lot of interface generation work in the last couple of years, and it goes really fast, right, Deepak? The more you do, you get deeply involved. He has, and it's great, he has his doctorate in EE, so some of you are EEs, and he went to ASU, so he sweated through every single year in the heat down there at ASU, which is a great campus and it's a great school. And he went to also Indian Institute in New Delhi, and he graduated there in 2013. So very smart individual you have here. I also challenge everybody to give him your best questions. And like Susan said at the beginning of the call, if you caught it, we want to give deference to our students to ask a couple questions first before the outstanding academic community behind us ask questions. But we're happy to stay on and do as much as we can to answer all the questions. So Deepak has received quite a few awards in the past, like the Energy Systems Integration Group Excellence Award and North American Synco Phaser Initiative for outstanding graduate student work. And also he has gotten another award, Power System Operation Corporation Award. So I think this is a great talk, and I know he'll do a great job, and I saw his work in the past. So we're privileged to have you today, Deepak, and I'm going to give you control. So thank you very much for everybody's attention, and put yourself on mute. That might help, but we want to keep it interactive. So we're all friends and family here. So feel free to ask a question, raise your hand. Susan's out there monitoring all of you. And we have a really good crowd today with about 35 people. So thanks.
Thanks a lot, Andy. And I hope you can see my slideshow in the full screen mode right now.
Yep, looks good.
Thank you, Susan. So it's a pleasure to be talking here. I gave a talk during the spring semester also, I think sometime in March, April. There it was more on the bulk power system connected inverter-based resources, how you control them, how you coordinate them, what kind of research challenges we're facing with that transformation that's happening. Today we'll be talking more about the distribution system, not core distribution system engineering, because my field of expertise is on transmission system, but what we'll be talking about is looking at how resources on the distribution system can impact the transmission system, and why, as transmission system engineers, transmission system operators, why we are getting more concerned about the distributed system resources and how we are trying to manage that challenge of the increasing penetration, and what kind of work that we are doing in trying to increase the observability, increase the controllability of these resources so that we can plan for more robust system operation. So one of the things that we have to set the stage for is, why are we really concerned about this modeling, and what is it about this modeling that we, or the operation of DER that we are really worried about? So what happens is, traditionally your distribution system network was passive in the sense that it was only load. So the flow of power was from the transmission down to distribution. But now, with distributed energy resources like rooftop PV, both at the individual household level and on, say, something like these big box stores or Walmart or Target, where you might have a lot of rooftop PV, then you now start getting a reduction in load at the distribution system end. But more so, what happens is, now if a transmission system event occurs, then you can have these distributed resources tripping in blocks. Essentially, what happens is, if you have a very small change in the transmission system voltage, so you see that here, if you have your voltage changing from 0.94 per unit to 0.89 per unit, which is essentially a 5% change in transmission system voltage, you can go from a state where all the DER are connected to a state where 80% of the DER trips out. And if this can occur on a wide enough area, then now you have transmission system events that would usually not cause a trip in generation, but that will now happen, which means that transmission system planners have to be able to have a visibility of the tripping that can occur. Further, what happens is, the stripping is in a way nonlinear. So if you just see, the voltage is reduced in a linear sense, where you have a 5% decrease linearly, but you can see that the tripping that occurs is nonlinear, where the spacing between these trips is not really in equal increments. So having a visibility of this nonlinear tripping is something that is a challenge for transmission planners, because they can't really represent the entire distribution system in detail, because that will just mean they're representing a very large system, and it will take ages to really solve one simulation. So the majority of the research work that we're doing is to try to understand how we can get a visibility of the stripping that can occur on the distribution side to enable transmission planners. So we'll split this aspect now into three different sections, where first section is about the model, second section is about parameterization of that model, and the third section is about the system impact that can come up. So taking the model itself. Now, there's a lot of text here on this slide, but we don't need to go through all of them. The main thing to consider is that transmission system analysis is usually carried out in something called a positive sequence simulation software. Now, what the positive sequence software is that even though the power network has three phases, your A, B, or C, or your red, blue, and yellow, however you denote them, even though there are these three phases, we assume at the transmission level that everything is balanced, that the voltage and current across all three phases are balanced, which means that all three phases in a way behave as a single phase. Because what happens on one phase, we can easily translate into the other two phases. So we represent the entire transmission network as a single phase, even though there are actually three phases. The other thing that happens is we assume that there's no network transient. So in your circuit theory 200 level course, basic circuit theory, you would have learned about things like inductors and capacitors and transient across the inductor, like the voltage across the inductor is L di by dt. The current through a capacitor can be C dV by dt. So those form of network transients for the inductors and capacitors, we assume that they're very fast and they're stable, which means that instead of representing the inductor through its transient, we represent it as an algebraic function, where we represent it similar to Ohm's law, where we say V is equal to IR for a resistive network. We do the same thing for an inductor or capacitor. So we don't have a time varying transient of the voltage. And we assume that everything is around fundamental frequency, in the sense that if you have a 60 Hertz system, we assume that most of the disturbances would be around 5 Hertz, around 60 Hertz, so that you can have a phasor-based approach for representing this behavior. All of this is done to aid the computational challenge and to ensure that we have a much more robust and fast simulation environment that we can really study very large systems. But what happens with distributed energy resources is that this degree of imbalance that is there, which is assumed to be low, can actually now be large, because if you even consider a three-phase DER, they can trip on unbalanced voltage, which means that if you have even a small level of imbalance, you can have a large amount of DER tripping. And also, single-phase faults are usually more common in the transmission system rather than three-phase faults. Thankfully, that is so, because a three-phase fault can cause a lot of damage. But even though a single-phase fault is more common, what happens is that DER on multiple phases, and this could be single-phase DER, can now get impacted because of a single-phase fault, which further leads to the imbalance that occurs and further leads to the transient. So there is a lot of approximation that we have to do based upon engineering judgment in order to consider these various factors while representing them into something called a positive sequence analysis. So the model that we use is an aggregated model. You essentially have your substation represented, and then you have a substation transformer, and then you have one level of a three-phase DER represented, and then you have an equivalent feeder to represent your distribution network, and then you have lumped loads considered at the bottom end of this equivalent feeder, wherein these loads could represent different forms of motor load that are there on feeders, lighting load, air conditioner load, pump load. They could represent behind the meter DER, so essentially rooftop PV that is considered behind the meter, they can represent them. And it can also represent different forms of DER that may or may not be netted with load. Now, we know that this representation is not perfectly accurate. We know that it is only reasonably accurate. But at the same time, we should also be aware that it doesn't need to be perfectly accurate. So a question may ask or may arise in your mind that how can we say that a model does not need to be perfectly accurate when all this while we've been talking about the need for good models and the need for representing this behavior well in a mathematical framework? So isn't this not a contradiction that we are saying that the model does not need to be perfectly accurate? And that's a very valid question, but that's not a contradiction. The reason for that is that we recognize that if we have to represent this feeder in detail, and I'll show you on the next slide how a big feeder looks like, we recognize that if we have to represent this feeder in detail, then it can really take us a long time to get one simulation done. But instead, if we use this aggregated model and the inference that we obtain from the use of this model, so let's say we are using this model and we understand with the use of this aggregated model that when you have a transmission system event, maybe 30% of the DER will trip. And let's say when we use a detailed model, instead of saying that 30% of the DER will trip, let's say it says that 25% only will trip or 35% will trip. So within that margin of error, we are getting the same inference that the transmission planner knows that, hey, there is going to be this roughly 25 to 35% of DER that will trip, which means we can make mitigation actions for that. So if the inferences that we use from these detailed models do not change whether we use a detailed model or an aggregated model, then an aggregated model is sufficient for the transmission planning purpose. So it doesn't need to be accurate, it needs to be sufficient. And that is where a lot of the research goes to identify under what circumstances is sufficiency met, how do we parameterize all of these components in this aggregated model to meet that sufficiency criteria so that we could make good planning studies. And the challenge still persists though, right? Because if you consider this is how one of a feeder may look like in the distribution network. This is just one feeder, and remember that in a network of the size of say something like the Eastern Interconnection in the US, or the Western interconnection, there could be more than 10,000 such feeders connected in the network. So we don't want to be representing each of them. But an actual feeder has things like regulators, it has things like capacitor banks, which control the voltage. There can be a variation in voltage across the feeder, as you see here, where this is a substation, and each node in the feeder can have a different variation of voltage profile across the entire network. And all of that needs to be represented by the simplistic model, wherein your substation is still represented, but now you have to combine all of the elements here into just these few elements that we have. And we have to essentially ensure that this entire voltage profile that you see here is represented in a way by a single phase RMS voltage profile, and it's still able to provide all of the characteristics that elements inside the feeder who would use each of these individual voltage levels to behave. We have to ensure that the characteristic of this feeder is represented by using this aggregated model. So we know that we have to use aggregated models. We understand that the sufficiency criteria has to be met. But now the challenge is trying to map all of this behavior from this detailed feeder, like this voltage profile and the associated impacts, into something called this aggregated model and this simplistic voltage profile that we would see when you move from substation down to the load bus. So one such model that we have to represent the behavior of these DER is what is called as the DER_A model. So this is a public document available from EPRI. Feel free to go to our website and download this to learn more about this model. But essentially what this model is it tries to capture the dynamic behavior of a lot of DER in the feeder and represent them in an aggregated fashion. So depending upon the percentage of DER that are providing frequency control, percentage of DER that are providing voltage control, some of them may be providing power factor control. They have different levels of tripping in terms of voltage. So voltage going below a certain level for a certain amount of time, they would have different levels of tripping. They might have different ways in which they recover from a fault. So post-fault active power recovery, they have different ways of doing that. And they need to be represented in a robust manner in terms of numerical behavior with respect to the bulk power system. So feel free to take a look more about this model in this document and understand how the various aspects of these models fit together. What we will be focusing on in this particular presentation is this trip characteristic. And the reason to focus on that is because majority of the DER that are located in a lot of feeders today don't really have this kind of behavior where they provide frequency control. They don't have the kind of behavior where they may provide proportional voltage control, but instead they are pretty much constant active power devices where, and if you consider most of them being PV, then depending upon how much sun is shining in terms of the radiance from the sun, depending upon that, they will generate a level of active power, which will be directly injected into the network. But if the transmission voltage drops, or if the transmission voltage changes, they will start to trip. So remember the stripping diagram which I showed on the first slide, where you have that nonlinear trip coming about with different levels of voltage. That is the behavior that is represented by most of the DER on the feeder today. So the aim is to first try to parameterize this trip logic within this aggregated model so that transmission planners can start getting a visibility into some of those tripping that can occur. That doesn't mean to say that things like voltage control and proportional voltage control, frequency control or proportional voltage control are not important and they don't need to be parameterized. It's just the priority in which we are addressing this parameterization challenge. So let's talk about parameterization. Now, before we talk about parameterization, though, it makes sense to have this slide in mind. And this is something that will be useful to you in your entire career if you are doing simulations with respect to mathematical models in the power system or any other simulation environment. It doesn't need to be only electrical engineering power system. If you're doing something in mechanical like fluid dynamics, or if you're doing something in any other field that you have, and you are representing various natural phenomena or various actual devices in mathematical models, then it's important to understand that all mathematical models have limitations. There's no real model, mathematical model, which we can construct, which we can definitely say has no limitation at all. And if we do construct that, it just means that to study even 1 second of simulation time, you might need close to 10 hours of actual time. So keeping that in mind, all mathematical models that we would use have limitations. Some of them are useful based upon how they are structured, based upon how they are developed, based upon how they are modeled. But even amongst them, they are only useful if they are parameterized properly. So you could have the most detailed model you can ever construct, but if you don't put good values for the parameters in that detailed model is as good as a useless model. So these are some things to be kept in mind when we talk about models, that parameterization plays a very crucial role in ensuring that the model accuracy is reasonable enough for the study that you're carrying out. So we revisit that diagram that we had showed on the first slide, which showed the nonlinear tripping. So now if we translate this kind of a time domain characteristic into a characteristic that still keeps the y-axis the same. So the y-axis is still the total amount of DER power, but rather than having time on the y-axis, we have these voltage thresholds on the y-axis. So now we are trying to characterize that for each of these voltage thresholds, how much DER is able to ride through the event and remain connected. This is, of course, arrows behind this legend here. And that can translate into this kind of a characteristic. Now, you might first say that, hey, I can draw a best fit line using maybe a least squares estimate or something like that, and really get a representation of the sufficiency of tripping of this model. But this representation of the tripping is for one given configuration of DER. In reality, what can happen is when you're looking at it from a transmission planner perspective, a transmission planner doesn't have visibility into the distribution system, which means that they don't know where the DER is connected on the distribution feeder node. They don't know what is the type of DER which is connected, whether it's three-phase or single-phase. They don't know whether the DER is clustered at some points or distributed across the feeder. So given that they don't know all of these uncertainties, if we actually now repeat the same simulation or the same exercise where we have a voltage variation of 5%, then if we extrapolate or we go from this one scenario where we had one configuration of DER, which could be represented by a least squares line, but if we now play in all of these uncertainties and we take various combinations of the DER location, then we actually get a representation of a trip characteristic, which is in this format. And now you can see the variation that is there at each voltage level itself. Pretty much instead of having one single point here, you have a host of points which would be aligned at a single voltage level. And this is the kind of the DER representation that we took, wherein depending upon the ratio of the DER after the voltage, depending upon the voltage level, the number of events that can occur or the occurrences of the tripping that can occur has a representation that is pretty much varied. What this means is, let's say if you consider this point here or this vertical line here, it means that depending upon how the DER is spread out across the feeder, a voltage level of 0.98 per unit can result in either 60% of the DER tripping, or it can result in no DER tripping. So there's this wide variation of what DER recovery that can happen in terms of understanding how this DER would behave for a transmission level event. And this is the core of the parameterization challenge that we want to address, that given the amount of uncertainty that is there, how do we bring that uncertainty to a transmission planner and give them a best guess estimate? So what happens?
So Deepak, so question for you in that regard. You know, there's lots of ways that we can talk about this from a transmission side. Does that, you know, will that give deference to the transmission plan in the future to, you know, install 1 megawatt batteries all over the place? Or is it a matter of, as you go denser, there will be more requirements for energy storage at some point on the distribution side? Where those get integrated, of course, is, you know, behind the meter, in front of the meter. Those are really complicated questions. So this is really interesting because it just shows that densification increases rather than decreases kind of the tripping model. I mean, we all talk about, and we continue to see money flowing into the densification, the electrification, but what this proves here is that, you know, we will see an increase in complications on these trip models that you have as voltage variance change.
Exactly. And not just voltage variance, it's also the increase in complexity as you have different types of DER coming in. Like, for example, a DER may have a lifetime of maybe 20 years, but in that 20 years period, the standards would change. So now at a given point in time, one particular feeder may have DER which follow 3 different standards. So let's say even if you go from 2003 to 2023. So 2003 was in a way when the first IEEE 1547 standard came into play. So the DER that connected after that would follow 2003 standard. But then there was an amendment in 2014, there was an amendment in 2018, there's an amendment in 2020. So now when you go until 2023, you can have DER that follow all 3 standards spread out across the feeder, and being able, and they all have different kinds of characteristics. So the challenge now comes about from the transmission planning perspective is, without going into all or without really modeling every DER or every feeder in detail, is there a way we can still represent these characteristics in an aggregated format so that we still get a picture of what's happening and also maintain our computational efficiency in running the various studies? It also goes about with respect to the type of DER, the type of load, the presence of capacitor banks, the type of voltage event, because all of this play a role in how the DER can behave during an event that occurs on the transmission system. And actually, out of these 6 categories that are here, a transmission planner has minimal to zero information on 5 of them, because they are all well within the distribution system within which the transmission planner may not have visibility into. And the transmission planner may only have information on the type of voltage event that has occurred on the transmission side. So essentially, we have a black box distribution system model, and we are trying to identify how that model will behave despite these various uncertainties that are there. Can we really understand how that model will behave so that when I'm doing a transmission planning study, I can make a reasonable enough judgment for the behavior of my system? And we have some work, I mean, the research work that we've been doing here at EPRI, pretty much we can follow some guidelines, you know, in order to obtain some of these parameter settings. And the process that we are using is first identify what is the interconnection standard that is there in the distribution feeder. Majority of these interconnection standards may be derived from IEEE 1547. So get an understanding of what is the distribution standard that is being used, because a lot of the aggregated model parameters can directly be obtained from this standard. Now, we're not recommending that everyone has to construct a detailed model of the feeder in a distribution analysis software. That's where a lot of the EPRI research goes, is in doing these detailed studies in-house at EPRI, but then combining all of the studies across different footprints to really understand if there are a generalization of parameters that we can derive, and then provide those general parameters to various utilities so that they don't need to really do a lot of the detailed analysis. And from EPRI side, we provide the thought process and the technology transfer and the learnings to the distribution utilities, to the transmission utilities, so that they can make use of these results that we have in making their efficiency or improving their efficiency in their study process. So the approach that we take is, once we have this detailed model constructed, we construct this detailed feeder. We do a lot of random studies on this feeder in terms of the location of the DER, in terms of the tripping characteristics that we have. And we really look at it for different kinds of feeders, different families of feeders, and then we collate them together to derive the tripping characteristic of the aggregated model. And once we have this tripping characteristic, we then derive a set of generic parameters that we can then say that if you use these generic parameters, you are going to get a representation of the behavior of DER in the system, which you can then use for your planning studies. An example or proof of concept of this was a feeder that we took up from Arizona, where the feeder is purely urban residential. So pretty much rooftop PV is what is the DER which is in that feeder. There is a large variation between the peak load and the minimum load, pretty much 8 megawatt or 7 megawatt of variation in the peak load versus the minimum load. And then there is not much of imbalance. There's only a slight imbalance across the various phases. And what we assumed in this analysis was that because the feeder is purely urban residential, we assumed that most of the DER is going to be residential, which means single phase. We made an assumption that let's say that each home in the feeder would add a PV panel whose rating would be roughly 50% of their peak load, because that would be based upon the available rooftop space, the orientation towards sun, the inclination of the roof, and things like that. And then basically averaging them across all the loads also. We also assume that peak load can usually occur during evening to nighttime. This is, of course, a pre-pandemic stage wherein folks would go to the office in the morning, children would be at school, daycare, whatnot, but everybody comes back home at around afternoon, evening time, when all the load kicks in at home, the air conditioners kick in, the ovens may kick in, and TV kicks in, and things like that, right? So peak load will tend to occur during later half of the day towards the evening, late evening, night. But the maximum PV output would occur during the daytime or towards mid-afternoon, which means that the maximum PV output would occur during the minimum load period. So that's very important to consider the coincidence of PV to load, because that has an impact on how the dynamic behavior of the system would be. So when we do that, when we take into consideration the amount of PV, the rating that we have, we see that the total DER will amount to 50% of peak load, but it actually amounts to 282% of minimum load, which means that if there is a situation that every house puts a 50% rating PV panel during a minimum load period, there could be a reverse flow of 282%, or 182% because it's 282% off the load. There could be a reverse flow of 182%, which in this case was around 3 megawatts, back into the transmission network. And that is something which is very important for transmission planners to consider, because now if this occurs at every feeder, at every substation, it means it will change the way in which we operate the transmission system, because now every distribution feeder becomes the generation source in providing power back to the transmission network, whereas previously there were only load sources. And what will happen is during the day, as you transition from morning to afternoon to evening, this will shift from the distribution system being a load in the morning, being a generation source in the afternoon, and going back to being a load in the evening, which means that the flexibility of the transmission system has to drastically improve in order to take care of these changes. What else will happen is the dynamic behavior of the system at each of these points in time can be different, which means the number of scenarios that a transmission planner has to study can now become three times the number of scenarios that they study today. And that drastically increases the number of studies they need to do, which means they need computationally efficient models and reasonably sufficient accurate models for each of these scenarios. So for the study that we did in Arizona, you see that the voltage profile at minimum load without DER and the voltage profile at peak load, at minimum load with DER, there is a distinct rise in voltage profile because inside the distribution feeder, there is generation coming about, so the net load is increasing. Lower the load, the higher the voltage profile occurs. And the concern is that if there are now faults on the transmission network, will those DER be able to write through or not? So as part of our detailed studies, we see that there's a wide variation of tripping that can occur due to the location of the individual DER. This was something that we saw in the previous slides also, that for a given level of voltage, you could either have only 20 to 30% of the DER that comes back after the event, or you could have close to 95% of DER that comes back after the event. And pretty much you see that the response is quite widely distributed, and it's even more so for a high voltage side. And we saw that voltages tend to rise as you have more DER coming in, which means that for a small rise in voltage where this is a voltage swell that occurred, maybe because of a loss of load somewhere else in the system where voltage suddenly rises, you can have this tripping behavior that occurs where in one place you could have all the DER riding through, whereas in another feeder, you could have only 20% of the DER that were able to ride through. So we need to take this into consideration now while we parameterize our positive sequence model. The concept that we use to parameterize the positive sequence model is to walk through how a DER would trip, wherein we say that let's say that the first inverter to trip is likely located towards the tail of the feeder, because that is where there is minimum amount of voltage control, so the voltage can vary quite a bit. The last inverter to trip is located towards the head of the feeder because that's closer towards the substation where the voltage can be a little bit more stiff. And the first inverter would trip when the tail of the feeder is below 0.88 per unit, but the head of the feeder is above 0.88 per unit because there's voltage drop across the feeder. The last inverter would trip when the head of the feeder is 0.88 per unit. So it's essentially solving Kirchhoff's voltage law across the feeder for different points in time and for different voltage levels, and identifying at what are the values of voltage at which the various DER would trip. We take this to the positive sequence environment, wherein now if we assume a downward trend of voltage profile, which can happen during the fault. It may not happen in steady state because that is when you have an upward trend of voltage profile, but during the fault, when the voltage drops on the transmission side, you can have a downward trend of voltage profile in the distribution feeder itself, which means that you can assume that the first instance of tripping in the DERA model occurs when the voltage is above 0.88 at the head of the feeder, and the last occurs at a value which subtracts the feeder drop. So again, this is probably too much detail, technical detail for a seminar like this, and feel free to send me an email to get to know more about these details. I can refer you to some reports and papers that we have that go into more of these details. But essentially, if we now use this logic of taking into consideration the voltage drop across the feeder, taking into consideration where and when DER would trip, we can get a representation, or we can parameterize these positive sequence aggregated models. And these are just rules of thumb that we derive for parameterizing this model based upon different interconnection standards, whether it's 1547-2003, whether it's California Rule 21, which is similar to 1547-2018 Category 3, or 1547-2018 Category 2. And depending upon which jurisdiction these DER are located in, they can parameterize the model based upon these kind of representations. And if you do that, we can actually start getting a trend of representation of the DER. So although the DERA model has a linear characteristic, but we see that depending upon how you parameterize it, you can get a representation of the amount of DER that trips, which is denoted by the black dots here, from the positive sequence domain, and they roughly lie within the characteristics that we obtained for the detailed feeder model. And this is for two sets of analysis of two feeders, wherein one had a more gradual drop-off, one had a more sharp drop-off, and we can really represent that characteristic. This doesn't mean to say that this will be valid in all scenarios. This is where research still needs to be carried out to identify under what scenarios these are valid, under what scenarios this kind of parameterization won't be valid. But preliminary results are encouraging with the use of these aggregated models and take into consideration these concepts of parameterization, that you can get a representation of the behavior of DER from a transmission planning perspective. So we'll take two examples to really identify why this parameterization is important and why it is so important to consider good values for these various stripping characteristics. So assume that you have a scenario where we have a utility member system. We work with one of the members that we have, and we say that there is total amount of DER in that area is around 3,000 megawatts. This is not at a single substation. This is a bunch of substations in a given area in the system. You can consider the area to be few counties in a state, which can sometimes be an entire state also, depending upon how big a transmission system we are considering, but consider it to be around 3,000 megawatts. And we have around 700 megawatt of headroom available in this area in terms of generation. And the goal is to study what will happen if this area disconnects from the rest of the system. So we have our DERA model, which says that all the DER would trip if the voltage goes below 0.89 per unit for 2 seconds, and it would trip if the voltage goes above 1.2 per unit for 2 seconds. So the goal is that if this entire area disconnects from the rest of the system, can this area continue to survive and operate in a stable manner with this DER present? And the reason it's important to do these studies from a planning criteria is because supposing there is an extreme event that requires this area to be disconnected. Let's say there's a tornado that goes through that region and really causes those transmission lines to trip. Then we need to understand if that remaining area can survive. Now, as we trip the area or disconnect the area was importing power from the remaining areas because it was a generation deficit area. Although we have headroom available, but it results in a deficit of around 938 megawatts. And we see that even if you have this kind of representation, because there is DER, which is located in this network, and because the DER has headroom available, we can call upon the DER to provide more support when there is a disturbance or when there is a disconnection that occurs in this region. Now, however, this is not always the case. What happens is, supposing we first apply a fault and then we trip, then there is a large amount of instability that manifests and all the DER trip in that region, which means that now an area which was deficit in generation will become even more deficit in generation, and that entire area could become unstable and collapse. So we have to really pay close attention to parameterization here, because let's say if this DERA model was not parameterized to showcase the tripping that occurs. So if you see here, the voltage stayed below 0.89 per unit for greater than 2 seconds when the DER finally tripped. So let's say that you didn't parameterize the model to take this into consideration, or you didn't even represent the DERA with this kind of a voltage trip, then you would have assumed that when you're doing a transmission study, that, oh, everything is going to be fine and we will continue to remain stable, which means we don't have to plan for this kind of an event occurring. But having this model parameterized in a good way really brings to light all of these instabilities that may occur. I'll quickly run through another parameterization example that we have to showcase why this is important. So we spoke about transmission system and single-phase faults previously, and we spoke about how single-phase faults are more common than three-phase faults. Now, in a lot of your Power System 101 classes, you might have heard about different winding configurations of transformers, depending upon whether there is a primary side star winding or a secondary side delta winding, and so on, and how the effects of voltage and current on both sides of these windings can be different depending upon the winding configuration. We also said that positive sequence models are primarily balanced three-phase models, which means that can they really represent this imbalance that may occur because of a single-phase fault? If we consider a simple example of a system where you have a delta star winding on these transformers at the substation, then it's important to understand how a propagation of a single-phase fault occurs when it occurs at the transmission level. So if a fault occurs at the transmission level, you might be, you can represent something called a sequence diagram in how the various phases of the circuit and the sequence of the circuit will be connected. And when you have a transformer which is star-star connected, you have a closed circuit for zero sequence current to flow. But when you have a transformer which is delta star connected, then you have an open circuit for zero sequence current, and you have a change in the angle that the load sees because of the phase shift between the delta and star winding. What that will result in is it will change the way in which the load, that is the DER in this case also, will see that single phase fault, and it will differ between whether the transformer is star-star connected or delta-star connected. And what really happens is if the transformer is star-star connected, you will have a lower voltage at the load end. You will see more voltage drop at the load end, which means you will see more DER tripping. But if the transformer is delta star connected, you will see a voltage drop on two phases, but the voltage drop level will be higher, which means that DER on two phases now can be potentially impacted as opposed to when there was a star-star connection. And what that will mean is if you have a delta star connection, because there are DER on two phases that can be impacted, you can have more DER tripping than you might have actually predicted for the single phase fault. And not just DER tripping from a single phase DER perspective, you can even have three-phase DER that trip because they would trip on unbalanced voltage, which means that in a positive sequence simulation, you now need to represent more DER tripping for a higher voltage value, which is contradictory to what happens when you have a three-phase fault. But by, apologies for the template here, which really covered this, but essentially by playing around with the parameterization of the model, you can actually now construct a parallel trip characteristic in this DERA model, wherein for three-phase events, you follow the black line, but for single-phase events, you follow the green line. The same thing we can do for two feeders. There's a paper that we wrote on this, so feel free to access that. And depending upon what event you are considering, you change the way in which the model behaves in characterizing the trip behavior of the system. And where that is important to consider is if you now see this at a transmission level, where we had a system where we had around 14 gigawatt of DER applied on a system throughout the entire network, and we applied an event, a single phase event in the middle of the transmission network, and you see that if you have a three-phase fault, then the DER trips in a certain manner as shown by the blue line, and it's what we would see for a detailed distribution network also. But if you don't change the trip characteristics and you apply the same trip characteristics but apply a single phase fault, some cases the model may show the same amount of DER tripping. In some cases, it may actually show that no DER trips at all for a different line. But if you actually parameterize the model appropriately to represent the single phase tripping characteristic, then it would actually show you more DER tripping, which is what a transmission planner needs to see. So if you say this case where a transmission planner applied this fault and saw that, oh, okay, for the single phase event, no DER trips, which means they're all good. But in reality, for the same single phase event, close to 800 megawatt of DER could have tripped across the entire network. And the transmission planner needs to be able to see this tripping occurring so that they can plan for this. So that's where parameterization also plays a role. And this is the kind of system impact we can expect to see from DER, and being able to model it, being able to represent it is extremely important. So I'll just close off with saying that we recognize that there is a challenge in both modeling and parameterization of these aggregated models, because from a transmission planning perspective, we have limited visibility of what goes on in the distribution system. And it's essentially a black box that we want to parameterize. But by doing a lot of studies and by really considering these various scenarios, we have been able to build up a generalized set of parameters that show promising results. They're by no means, however, a closed set of generalized parameters. There's still more research work to be done. There's a lot of work to be done to understand the interaction between load and DER and how they may impact the behavior of DER and the aggregated model. So that's something that we're still continuing to work on. And it's possible that at the transmission side, we could get unexpected results with DER tripping in blocks, but it's not to be considered as something which is a simulation artifact, because in reality, DER may actually trip in blocks, and it's important for us to consider that in our planning studies. Some of the questions that we are still have open and still a lot of active research work to be.
That was fantastic. Thank you very much. And now we have like 42 people on the call, so that's great. Very nice, large attendance. So that was interesting. One thing you did point out, and I'll just kick off the question. So you said that in a large model, you might not see some of these interdependencies as well. And that's fascinating to me, because I think, you know, when I work with California Public Utility Commission and I see kind of how they're rolling out their DER strategy for microgrids, you know, it's obvious that it's not really planned. What type of case studies are we doing at this juncture that kind of speaks to the volume of the issue? Because, you know, it's just clearly not enough as a DER complex on, you know, we could all solve this putting in another, you know, 3,000 megawatts here in California. But when we start looking at the granularity of the city complex and all the work that people want to get done, this is very, very complicated. So what is the one thing you could say that's going to get this point across to regulators?
So one aspect here is firstly showing that there can be so much variation in DER behavior that it's sometimes not possible to capture everything in a model. But at the same time, it's also important to understand that we shouldn't be expecting a single model or a single simulation to capture all the behavior that's possible, because that just means that it will not be computationally efficient. So things like co-simulation techniques, aspects like co-simulation techniques can be important here to really split up the way in which we do our modeling and simulation for different systems, so that we can capture one set of detail in the distribution system, maybe to show its impact on the transmission. But there it's also important to understand that it's important to really identify when and where co-simulation would be required and how to identify those use cases. So that's where some research potential is there in really being able to identify that. I think what else comes about is really applying good engineering judgment to carry out a set of sensitivity studies and to define the sensitivity study boundary to really go from a conservative approach to maybe an optimistic approach and find out what lies in between, and then collect data with respect to the various levels of interconnection that is coming in at the distribution level, so that one of the main challenges that we saw at the transmission level is this lack of observability into what is happening in the distribution system. So collecting the data at the distribution system environment and coordinating with transmission planners to really transfer the data will really help in providing or increasing more visibility.
Great. Let's open up the floor to others. So does anybody on the floor have any questions for Deepak from the students? I'm sure there's some out there. I know not everybody's on their camera, so it's a little hard, but if you do get on your camera, Deepak could see you, which is great. Any questions? See, Revis is out there. Hi, Revis. All right, anybody else have any questions? This is a lot. This is a pretty packed, very technical presentation, which is great for me, and it's been great, I'm sure, for others. But anybody else have any questions? James, anybody?
Just an observation, if I may. It seems that the benefit of DER spread across multiple distribution circuits is a blessing for the grid. However, DER spread across a large number of distribution circuits is a curse for the grid because it is impacted by so many things that the grid operators have no control over, notably weather. When a cloud system moves across a distribution area, which is geographic, the load drop occurs across that area. So it's hard to say it's a single event.
Yeah, the other thing that can occur there is, as you said, it's both a blessing and a curse, because it spread out across means that the possibility of one particular feeder or substation failing may not cause that much of an impact on the system. But at the same time, what can happen now is if it's so much spread out, say you have a voltage event that occurs, let's say at the 230 kV transmission level, or maybe even at the 500 kV transmission level, that can be, or that voltage event may be now felt across a wide area. And what that means is that one voltage event at that higher transmission level can really cause a wide amount of DER to really react to that if those settings are not configured properly, which means that a single fault at the transmission level could really now result in a large amount of DER tripping, which is something which we are very concerned about from the transmission side. That the events that we study for, the events that we plan for, so especially for frequency, we usually plan for largest generation loss, which used to be the single largest generator that trips. We plan for having enough amount of reserve to be able to cater to that single largest generation trip. But now, if a large amount of DER is going to trip because of a voltage event, characterizing the amount of DER that would trip and understanding if that will be larger than the single largest generator is something that's going to be a real challenge for us to overcome, because that will play a role in understanding how much reserves we keep on the system.
Okay, cool. I want to actually.
I wonder if I can make another observation. I chaired the A revisions to 1547 and 1547.1. And the three things that we had to address that made it obvious that DER standards were not finished was, one, to allow DER to provide reactive R flow, two, for the DER to be able to ride through higher voltage depressions for longer periods of time, and three, for the window on frequency drop had to be widened and allowed also for ride through.
Mm-hmm. Yeah, so thanks, Jim. Yeah, so Jens, I don't know if, I'm sure you know Jens Bomer from EPRI, who's been leading a lot of the 1547 related activities. A lot of our distribution, DER impact studies that we do for our transmission members focuses along that point, that showcasing how if you move from 1547-2003 strict voltage setting and move towards a 1547-2018 Cat 2 or Category 3 setting, what kind of benefit one can get at the transmission system by moving towards those newer standard settings is something that we have done work on.
If you would give my regards to Jens, I've worked with him for years on the 1547 standards.
Absolutely, we'll do so.
Okay, Deepak, Revis James had a couple questions. The first one is kind of long. He asked, would it be correct to characterize most behind the meter DER as A, customer controlled, and B, designed to protect the resource with little coordination with the grid? greater
Yes,
than he has,
yes.
he is greater than he has a greater sign, arrow pointing to the right, that DER is fundamentally a variable generation resource?
Yes, so yes, yes to all three. That it's usually designed to protect themselves and not really coordinated or not potentially coordinated. And that's something where standardization can help, because a lot of times DER, which are connected to the distribution system, is also off-the-shelf DER, which means that the inverter would be, you just buy it off the shelf, whatever default settings are applied there would usually be connected. Now, there is an increase in distribution system level studies that really look towards this kind of coordination and really providing guidance on how these parameters of these DER can be set at the individual level to ensure that they don't fight with each other, they don't cause oscillations with each other in terms of how they behave. I'm not sure if I answered all parts of that question, but if I didn't, feel free to send it to me by email and I can definitely answer it point by point.
Hey, Susan and Andrew, this is Revis. I thought I might summarize the other questions I had in one single.
Go
If you
ahead.
allow me to do that.
Yep.
Yeah, Deepak, thank you for an excellent presentation. I very much appreciate it. I had a series of other questions which can be relayed to you later, but in essence, I think this first question illustrates an issue that I believe EPRI was working on a number of years ago, which is basically how the system, whether it's either the transmission system, distribution system, or whether the generation portfolio can be modified to absorb the impact of more variable generation. You know, in those days, it was mainly focused on renewables, but I think even then it was the leading indicators of DER would fall into this category from a practical standpoint. So what I'm just wondering from your perspective, I don't know whether this is an area you have looked into in your research, but given the presence of this DER as an added source of variable generation in effect, I'm wondering what can be done in terms of transmission system planning to strengthen the system to absorb the impacts of that added variability. I'll just add a little parenthetical side comment. Back in the time when that work was done, looking more at renewables, the answers in those days tended to focus more on increasing the diversity and the location of generation assets in various places to absorb that. But I was just curious what your perspectives were as it relates to strengthening the transmission and distribution system.
Yeah, so I think where it will go towards is definitely now increasing the kind of services that each DER or transmission system inverter-based resource can provide. We no longer want to go down the route where they would really take all the power they can generate and really inject it to the system and inject that in a rigid manner. What we want to try to move towards is we want to try to get these inverter-based resources to provide different kinds of services, frequency response, voltage control, whether that frequency response is primary, fast frequency response, or what kind of time frame it is will depend on the inverter itself and the system in which they are operating in. Things like improved ride-through capability, coordination with battery energy storage system to flatten out the variability. So I think it will come down to now having each inverter-based resource having a stacked layer of services that they can provide to the system, which is easy to say from a technical perspective, but it's not very easy to implement because there are economic aspects that come into play there. There are policy aspects that come into play there. So I think this problem will now expand from just a general transient stability discussion into transient stability economic discussion, because say if you want them to provide frequency response service, then will they get paid for it? How much of headroom do they have to maintain? If they have to provide voltage control service, how much do they have to oversize their inverter to allow for that increased current to come in, and where does that fit into the economic aspect? So I think generally it will come down to requiring most of these inverters to provide more services, but the economic model that will allow for that to come in is something that's still to be done. Maybe for quarter 22 will help in that regard a little bit, where there is DER aggregators that can participate in the market and provide some of these services. So that will help socialize some of this variability and essentially flatten it out a bit.
I appreciate that answer. I'll just add a comment. I think it would be very productive if research were available that helped connect the technical implications for DER performance capabilities, these services you're referring to the financial impact. Because right now, I think the impacts related to grid stability or the interconnection between generation and transmission capabilities and the presence of variable generation are not really monetized in markets or in modeling. So as a result of that, these issues are only looked at after the fact. So the modeling you've done here could be connected to that in the future very productively, I think.
Yeah, we have an ongoing project here at EPRI, and I'm sure there are others at different organizations also, really looking at how to take the clauses and the aspects of work order 2222 and really link them to the way we would do our models, so link them to the way we would ask for different services and link them to the impact that they would have on the system. So that's something which is ongoing, which we could probably have a presentation at a future seminar.
Great, thanks for your response. Appreciate it.
Okay, one of our
Thank
students.
you so much.
Sorry to interrupt you. One of our current students, Laura Marsiglio, had a question. She said something she's not quite clear on is the difference between distribution and transmission. I know this is not directly related to the topic of your talk, but I think it would aid in my understanding.
Yeah, definitely. So there are few key differences between what we call distribution and transmission. One is the voltage level. Transmission system pretty much operates at higher voltage levels, maybe 230 kV, 500 kV, levels like that. So usually the way we split up our system, of course, this is not a one-size-fits-all demarcation, but generally we say anything above 69 kV is considered transmission system. Between 69 kV to 33 kV and 12 kV can be considered sub-transmission system or primary distribution in certain places. It's called that. Anything below 12 kV down the way to our supply at our household, which is usually 400 volt three-phase, 120 volt single-phase. Not exactly these round numbers. It's a little bit non-rounded, but that level is usually distribution system. So that primary difference is the voltage level. The secondary difference that comes up is the characteristic of the system itself. Transmission system, because of the higher voltage levels, the kind of conductors that are used for the representation of the system is predominantly inductive versus resistive, which means the inductive to resistive ratio is high. What that means is there is a decoupling between active power and reactive power, in the sense that active power doesn't impact voltage magnitude much, it's decoupled, but reactive power impacts voltage magnitude. As we come towards the distribution level, the inductive to resistive ratio starts reducing, and there can be times where the inductive to resistive ratio can be unity, which means that there is more coupling between active power and voltage and reactive power and angle. So that is a difference between the operational characteristics. What else happens at transmission level is pretty much we assume that almost all the load and all the generation is three-phase connected. Whereas when you come to the distribution level, if you come down to especially like household distribution level, you can have single-phase loads and single-phase generation. So there's more variety across the phases in terms of the difference between transmission distribution. So I've of course not covered all the differences, but these are some of the primary differences that we use, especially from a perspective of modeling and operation of transmission and distribution.
Okay, the next question in the chat is from, I hope I pronounced your name right, Balaji Ramasubramanian. Sorry, Subramanian. It's close. Yeah, it's close to your name. Can the parameterization also be extended to the MVDC or LVDC grids? And thank you for the presentation.
So the parameterization can definitely be extended, but when we start going into DC grid, one thing we need to start keeping in mind is essentially you lose the reactive power portion because the DC grid will not have a reactive power portion, but there's now a stronger coupling between active power, voltage, and angle. Not angle really, again, DC grid doesn't have an angle, but active power and voltage. So the concept of the parameterization can be extended to DC grids, but the implementation of the concept will now have to change because it now needs to take into consideration the change in the characteristic wherein you no longer have reactive power, you have everything from active power only, and it depends upon how the voltage is controlled. So, and definitely the concept can be carried over, especially the tripping aspect, because that's just voltage dependent. But these aspects of how you would control the reactive power, how you would do voltage support, how would you prioritize between doing active power versus voltage support? Will they be really symbiotic with each other? Those are things that have to be kept in mind when you start looking at parameterization in the DC grid.
That's all the questions I have in the chat. Go ahead, Andy.
Yeah, so we can open it up if anybody else has any questions. Otherwise, we'll say goodbye to Deepak, but he's here for you. Definitely have a couple more minutes left, but we want to get, this is your opportunity. So anybody else?
Yeah,
Will these PowerPoint slides be available?
Deepak, the question
yes, we can share. Okay, there's no problem at sharing. Susan, I've shared a PDF with you. Feel free to send that out if there's a. I don't know how you'll do it for the seminar talks, but if there's a way to do that, no worries.
Okay, great.
Okay, cool. Okay, somebody else was speaking too.
My personal thanks for an excellent presentation.
Thank you so much.
Okay, last call. Anybody else? Nick? Elias? Okay. All right. Well, Deepak, thank you very much for your time today and spending some time with us out of your busy day. And they are busy these days. So I think your email address is open to the students in case they get some inspiration later in the day. And thank you again for all your help, and thanks to everybody for attending. And we appreciate it very much. So I hope everybody has a good week. And thanks again for attending this seminar.
Thank you so much.
Thanks, everyone.
Okay, bye-bye.
Bye-bye.